Hello. Chris Lehto, a former F-16 fighter pilot, has released a couple of videos that he says debunk my debunks. He de-debunks the Gimbal video and the GoFast video. Now, I disagree with his analysis, and I'm going to explain why. Let's start with the GoFast analysis. Now, the majority of his criticism of this appears to be based on focus. He spends a lot of time explaining that he doesn't think that something can be 5 miles away in focus and 10 miles away in focus on this camera.
Is obvious to anyone who's ever flown these things is you can't focus at something 10 miles away and then focus at something 5 miles away. It just is not how physics works, right?
And he does a bunch of demonstrations along these lines. I could demonstrate the effect he's doing quite easily by holding up something halfway between the camera and my face. My face is in focus, but this thing which is halfway between them is not. So you could think my face is at 10 miles and this is at 5 miles, and so you can't be both in focus at the same time. But of course this isn't actually true in the broad sense of 10 miles and 5 miles being in focus at the same time. Like, here's a picture of Yosemite. This shows El Capitan, which is this big one in the front, which is 5 miles away from the camera, and it shows Half Dome, which is 10 miles away from the camera. And both of them are in perfect focus, and this is at 200 millimeters, so it's not a wide-angle lens, it's actually a zoom lens, so it's zoomed in. It's not zoomed in as much as the at-FLIR system, of course, but I also have a Nikon P900, which has a 2000 millimeter equivalent lens, which gives it pretty much the same field of view as the at-FLIR system, and I've modified it to take infrared images. It's shortwave infrared, not long-wave infrared, but it's still infrared. And I took it up to the lake, and I focused on the far shore of the lake, which was about 4 miles away. And then I moved the camera down, so I was looking at the near shore of the lake, which was about half a mile away. They were both in focus, even though I was at maximum zoom, full 2000 millimeter, 1 degree field of view. Both things are in focus. I did this for a bunch of other things. It's kind of difficult to do at ground level because you always get this heat, haze, and shimmering. It's a lot easier if you're higher up, but the point is, it's not impossible to get things in focus at the same time at 5 miles and 10 miles. Really, his experiments in the kitchen do not scale to larger scale. You can't take something on the order of feet like we have here, where things are not in focus, and scale that up to miles. Quite obviously, like this picture here, things are in focus. So it goes on from that to say that because they can't both be in focus, then the range value that's on screen must be wrong. And he doesn't really justify why it's wrong. So he's kind of basing this, I think, on this focus issue and then saying it must be wrong. But it's been 3 years now. No one else has ever suggested that this range value is wrong. Nobody seriously has brought it up. I think Lou Elizondo briefly mentioned it. But everybody, like all the other pilots who have looked at it up to this point, they've accepted it as far as I know. So I'm going to leave that one there because Chris himself has kind of said, there's a bit of doubt there.
Hey, this ain't no GoFast. What about the depth of field? Maybe the depth of field. Okay, let's try it on this one.
And let's move on to the more interesting one, the gimbal video. So Chris's argument here is that the object is not far away. I made the argument that it might be a jet that's far away. I think it's probably not an airliner. It could be, though. It might just be another F-18, but it could be something that's really far away, and we'll kind of get into that later. Now, Chris draws this diagram on his video here. This is an overhead diagram of the motion of the jet, and he was going to draw some lines of bearing which show you where the camera is looking. And it's fairly straightforward. He has 3 points. There's 2 shown here at the moment. There's point 1, and at that point it's pointing 53 degrees left. Point 2 is pointing 38 degrees left, and I think later on we'll get to point 3. Right here is pointing 21 degrees left. So 53, 38, 21. And these are just 10 seconds apart in the video. So we know a bunch of other things. We know how fast the jet is going. On screen, we have the speed. So 242 here. I think we take 241 as a good average because it goes from 240 to 242. So 241 knots. Now this is the calibrated airspeed. And this is an important distinction that you need to understand. There's a few types of ways of measuring airspeed, which is how fast you're moving relative to the air around you. The two important ones here are calibrated airspeed and true airspeed. True airspeed, as the name kind of suggests, is how actually fast you are moving relative to the air around you. So if there's like, a cloud here in the air and you zip past it, your speed relative to that cloud, which isn't moving, is your true airspeed. There's also calibrated airspeed, which is related to indicated airspeed, which is how fast your instruments tell you you are going. Indicated airspeed, they use these little pitot tubes, which measure the difference in pressure front and back, and they have these little chambers which figure out how fast you're moving. But the indicated airspeed varies with altitude. It's not the same as true airspeed. However, it's a useful number because it's the number in which all your V speeds are given. So you're like your stall speed and your various other speeds that you need, and various other maneuvering things. They're all given in this indicated airspeed, or rather calibrated airspeed, which is indicated airspeed corrected for the instrument errors. So we've got two airspeeds: calibrated airspeed, which is a number here, 241 we're going with, and we have true airspeed. You can convert between the two, and the way you do that is you take the altitude into account, because the altitude tells you what the pressure is based on a standard atmosphere, and we're just assuming standard atmosphere here. You take the calibrated airspeed and you take the altitude, you plug it into one of these calculators, and it comes out as being 350 knots. You can do that here. Here's 25,000 feet, calibrated airspeed 241, comes up. True airspeed 350 knots. So that's the number we need if we want to know how the actual distance it's moving in the air, as opposed to calibrated airspeed, which is an aerodynamic concept really, not the actual movement. So going back to Chris's video, he does some kind of rule of thumb based on his experience and knowledge, and says that there's a certain turn radius, standard rate of turn, which is 2-minute turn. It takes 2 minutes to go around a full 360, which means you go 3 degrees every second. So there's a standard rate of turn, 3 degrees per second. And he kind of knows what the radius would be. I think he puts it at 2.4 nautical miles radius. So from here, the center of this turn, to here, 2.4 nautical miles. He's got his scale here, 1 nautical mile. And we kind of know how fast we're moving and how far we're going. So I'm not sure how he did this exactly, but I guess it's a circle going around here. Doesn't look like quite a perfect circle, but it's probably close enough, really. So he starts here, plane's pointing upwards, goes to here, the plane is now round a bit to the right and over here. And he draws the line relative to the heading of the plane for the camera for each position. So here, 53 degrees from straight ahead, and the next one 38 degrees from straight ahead, and then the last one 21 degrees from straight ahead. And then he shows where they intersect, and it's pretty close. It's only like 3 miles away, so that doesn't seem to really line up with the hypothesis of a distant jet, does it? So what I did is I tried to replicate this, and the way I did it was I used GeoGebra, which is this nice little geometry program. You can just stick in all kinds of numbers and equations and do lines and intersections. And basically, I'm trying to do the exact same thing he was doing. So we've got right here, this is where the jet is starting. So this point 1 is the same as his point 1. Point 2 here is the same as his point 2. And point 3 is also the same as his point 3. And so you can see here we have 53 degrees, 38 degrees, 21 degrees. This is the circle around which the plane goes. And here I have the true airspeed at 350 knots. And I have the rate of turn set to 3 degrees per second. Now I'll explain at the end of the video what all these calculations are if you're interested in the math. But basically this is just essentially the same thing as Chris had, but in a more easily replicable form. So I could do things like I could say if the true airspeed was actually 450, what difference would it make? Not a lot of difference actually. So let's go back to 350, which is the actual airspeed. So this is all based upon a standard rate of turn of 3 degrees per second. So the plane is turning to the left 3 degrees every second. And it's traveling along this circle at 350 knots, true airspeed. What happens though if we had a smaller rate of turn? Or if we go down to say 2.5? Now you can see here already the makes the circle a bit bigger because we're not turning so much, and the lines of bearing of the camera kind of go out a little bit further, and the intersection is a little bit further. Now if you go out even further, things very quickly take a fairly dramatic turn. We go down to 2, so things are very far away now. Now here I've listed the intersections of these lines. So this is the first line of bearing, the second line of bearing, and the third line of bearing. So this is the intersections of 1 with 2, 1 with 3, and 2 with 3. So it's just kind of showing roughly where they all intersect. Probably the interesting one is this first one here, intersect 1, 2. So this is the first 10 seconds. And I have it called out here. The distance from here to here, 5.36 nautical miles with a rate of turn of 2.25. We go back to 3, which is what Chris was using, and it's only 3 miles away, 3 nautical miles, which obviously is a bit close. But anyway, what if it was even lower? What if it was all the way down to 2? Now we're going up to 8 nautical miles, which is kind of getting more like it, but it could be even lower than that. Like what about 1.8, 12 nautical miles? Or if it was like 1.5, 32 nautical miles, it's just all of a sudden gone really far away. And if we keep going down, it quickly pops into infinity. So the idea that it's close depends very much on the rate of turn. Now, Chris said it's a standard rate of turn, 3 degrees per second. But is it though? We can look at the angle on screen. We can look at the angle of the bank. So we know the bank angle, and we know the speed, and we know the altitude. But it turns out that's not that important, because rate of turn is just based on true airspeed. At least that's how I understand it. I found this chart, which shows an FA-18 as turn capabilities, and down here we have the rate of turn calculator. Over here we have true airspeed, and down here we have the rate of turn. So to figure out, we have bank angles with different lines here. So if we've got a bank angle of 30 degrees, what we do is we take the true airspeed over here, which was 350, so just under this 360 line. We go across until we intersect 30 degrees, and then we go down. And that brings us somewhere around, I guess, 1.75. Yeah, something like that. Maybe a little lower, 1.7, which is a kind of logarithmic scale here. What we can do is we can plug that into the equation here, 1.7, and it gives us 16 nautical miles away, the very first intersect for the first 10 seconds. And actually, over the first 10 seconds, it's not 30 degrees, it's actually 26 degrees if you measure the angle 26 degrees. So if it's 26 degrees, that will be a line somewhere over here. We can imagine this 350 coming across, meeting the 26 degree line over here, and then coming down. It's even closer to 1.5, so it could be something like 1.6. So let's go down to 1.6, and it's 30 nautical miles away. Could possibly even be slightly over. Right now we're getting into the kind of asymptotic range where things diverge very, very quickly. So if it was a little bit slower, it's 100 nautical miles. And if we look at the other intersection, it's not even intersecting now because it's so far away. We can drop down a little bit and poof, jumps to infinity. So the question here, I don't know the exact answer because I could be making some mistake here. I could be misusing this. I also used online calculators to do the same thing. We can take the let's see. We can use this as an online calculator to take 350 degrees, take a bank angle of say 26, calculate what we do. It's like 1.52 degrees per second, which if you stick that in to the equations here, 1.52 degrees per second, and I can actually edit it directly, I think. 1.52. 72 nautical miles. First intersection over the first 10 seconds. So I think there's some real questions here about Chris's analysis. Is it actually close? And perhaps we could resolve these questions. What is the actual rate of turn of an F-18 in level flight at 25,000 feet with a 26, 28 or 30 degree bank to the left? What will be the actual diameter of this circle, and how far along it will we actually move given our true airspeed? And what will these lines point at? Will they point at something that's close or something that's far away? Based on my calculations just now, using this chart, it seems like they're pointing at something that's far away. So let's try to resolve that. And I'd be happy to talk to Chris or anybody else regarding this, but I reached out on YouTube, and perhaps he didn't see my comments, but I haven't heard anything from him yet, but I'd be happy to talk about it and go over it. So I think the rest of his gimbal debunking thing is mostly about he thinks the glare doesn't look like what he would expect a glare to look like. But we've seen glares from planes, and they do have these sharp outlines. There's some by Dave Falch where he shows a glare that looks kind of similar. And I've done experiments myself with a little thermal camera, and you get this fairly sharp outline. It must be, I guess, something to do with the way thermal images work. You get a stark contrast and this kind of blob shape. But anyway, so my point here is this is just simple facts, and it's simple science and knowledge and mathematics that we should be able to come to some agreement on. It doesn't have to be like, I'm an expert or I'm not an expert, and you have to trust me or trust someone else. There should be a very straightforward answer to what is the rate of turn of this FA-18 in this situation. So let's figure that out. I mean, I'm thinking that it's more like 1.6 degrees per second based on this this diagram here, but perhaps I am misunderstanding it. Let's try to resolve it. Okay, so if you're still with me, I am going to go through this, just kind of explain what's actually going on, just the broad mathematics of it. So the first number I put in to GeoGebra was this rate of turn, and I stuck it at 3 originally, so let me just edit it back to 3. So that's degrees per second, 3 degrees per second. This turn 10 is how much it turns in 10 degrees, which is 30 degrees. And you see that down here. In 10 seconds, between 0.1 and 0.2, it has moved 30 degrees, and then it moves another 30 degrees to 0.3. The turn 360 duration is the number of seconds it takes to go around the circle. Is 120 for a 2-minute standard rate turn. 3 degrees per second gives you 120. And this number here, turn circ, is turn circumference. This is the circumference of this circle. So this is the calculation here that everything depends on. So you're going to make sure you got this right. So this is, if we take the true airspeed, divide it by 3,600, which is the number of seconds in an hour, that converts not nautical miles per hour into nautical miles per second. And then we multiply that by 120 seconds to get the length in nautical miles of the circumference of this circle. So it gives you 11.67, about 12 nautical miles around. You can then take the circumference and turn it into a radius by taking the turn circumference and divide it by 2 pi, because a circumference is 2 times pi times the radius. So that gives you a radius, which is the distance from the center to the jet, of 1.86. And then we use that to construct all these other things. So we construct a circle here. This, let's see, this C here is a circle centered on point C with a turn radius of turn radius. And then we can take the intersection of the 30-degree line with that circle, and it gives you 0.2, and the intersection of the 60-degree line with this circle gives you 0.3. So we can take each of these points, and now we have the angle of the camera to the left, and it's 53 degrees here. So we take the heading here at this point on the circle, go 53 degrees to the left. This gives you a line of bearing going over there. Take this one here, we take 38 degrees to the left of the tangent of the circle, gives you this line of bearing, and this point here, finally 21 degrees to the left of the tangent of the circle, and it gives you this line of bearing. So we've got the 3 lines of bearing, which are all the same as in Chris's diagram earlier. And then I'm simply taking the intersection between the lines here. So given that this is all computed from the rate of turn and the true airspeed, the only two variables we have here, other than 10-second intervals, we can then take the rate of turn and we can adjust it and see what effect it has. Now, obviously, if we go down to a 0 rate of turn, we're going in a straight line, and the circle flattens out. But we're interested in standard rate of turn. Looks like this. Looks like Chris's diagram. Rate of turn that's lower, like 1.8 or whatever. Things get to be much further away. Say 12 nautical miles there for 1.8, or 42 nautical miles for that, and down below 1.5, it's infinitely far away. So I'll place a link to this calculator so you can verify all this yourself, but all the math is here, just on the side panel. It's all very straightforward. You can do it yourself, and it's doing it with pencil and paper is great, but you get one diagram, and this way you can very easily experiment with differences, and you can see what a lot of difference a small thing will make. Probably lost most of the audience with that technical thing, but if you're still here listening, let's work it out. Let's figure out what's actually going on here. I'm open to being wrong, but I think I've raised a valid point here that probably should be addressed, and let's do it.